When we talk about artificial intelligence, it is tempting to picture a single monolithic algorithm. That is a category error. Artificial intelligence exists as a comprehensive field of scientific study, structurally analogous to physics. To successfully deploy modern AI in an enterprise setting, you have to understand the specific architecture of its subdisciplines. Look at this macro-level mapping. This outer boundary represents artificial intelligence itself, the primary container for all automated cognitive tasks. Tucked directly inside that boundary is machine learning, the first major subfield. Go one level deeper and you find deep learning, a highly specific subset operating entirely within machine learning. And right at the core, at the deepest intersection of these layers, is where we find large language models and generative AI. The defining factor that separates these layers is strictly determined by how each system processes and learns from data. Without this structural map, strategic planners risk solving enterprise problems with the wrong class of technology altogether. At the baseline, machine learning programs utilize input data to train a model, which can then predict outcomes on data it has never seen before. The most common approach is supervised learning. This paradigm is defined strictly by its reliance on explicitly labeled historical data. This Cartesian plane plots restaurant bills against tip amounts. Data is explicitly labeled: blue dots for pickups, yellow for deliveries. The supervised model predicts the next tip, compares it against known labels, and iteratively closes the error gap until highly accurate. The opposing paradigm is unsupervised learning. Instead of labeled inputs, it relies entirely on the ingestion of raw, unlabeled data. Here, employee tenure is plotted against income. Notice these points have no labels telling the model their gender or department. The model's sole function is discovering natural mathematical structures within the noise, drawing borders around dense clusters of similar data points. In practice, you can ask this model if a new hire mathematically aligns with the cluster representing fast-track employees, based purely on where they land in the distribution. An enterprise does not choose between supervised or unsupervised models based on software preference. The baseline architecture you deploy is dictated entirely by the structural availability of labeled data. Moving deeper into the taxonomy, we reach deep learning. It operates as a subset of machine learning, driven by an entirely different architecture. That architecture is the artificial neural network. Modeled loosely after the human brain, these networks arrange nodes into layers, and their predictive power scales exponentially with the density of these interconnected vertical columns. This depth solves a critical scaling problem. A major bank processes far too many daily transactions to manually label them as fraudulent or safe. Because neural networks can process complex abstractions, they enable a hybrid solution known as semi-supervised learning. First, human operators spend a fraction of their resources labeling just 5% of the transaction data. The model studies this microdata to learn the underlying abstract concepts of fraud. It then autonomously parses the remaining 95% of unlabeled data, outputting a fully sorted dataset on the other side. Network depth allows an enterprise to generate predictions across millions of records without linearly scaling the prohibitive cost of human data labeling. Within that deep learning layer, models fracture into two distinct operational paths, separated entirely by what they produce. The first path is discriminative modeling. These are systems engineered exclusively to find boundaries between existing categories. If you provide labeled data of different shapes, the discriminative model learns the relationship between those inputs, so it can classify future data into those exact predefined classes. Discriminative models are relied on to detect email spam, flag credit card fraud, or return statistical probabilities. Generative AI is the functional opposite. It is defined by its capacity to map underlying patterns to synthesize novelty. Instead of drawing boundaries, generative models ingest training data to extract underlying variables, like syntax, geometry, or pixel arrangements. When you submit a prompt, the model uses those variables to render a completely original artifact that never existed before. This is the architecture behind natural language generation, synthesized audio, original imagery, and functional code. This establishes a strict diagnostic rule. If the system outputs a classification, a probability, or a number, it is discriminative. If it synthesizes a novel artifact, it is generative. This brings us to large language models, sitting at the exact intersection of deep learning and generative AI. The defining architectural feature of an LLM is a strictly two-stage training process, beginning with the massive ingestion of training data. Phase 1 is pre-training. The model consumes vast, generalized volumes of data to learn common language structures and broad world logic. You can think of this like training a family pet. It learns basic behavioral commands, making it highly capable, but distinctly non-specialized. For an enterprise, this is a critical limitation. A broadly pre-trained model lacks the domain-specific rigor required to operate in highly technical industries. That necessitates Phase 2, fine-tuning. In this stage, smaller, highly specialized datasets are fed into that baseline model, adapting it for a strict specialist role. It is the equivalent of taking that well-trained family pet and putting them through rigorous, specialized schooling to become a police canine. This two-stage architecture dictates the macroeconomic ecosystem of modern AI. Large technology companies spend billions on the immense computing power required to build massive, generalist pre-trained foundation layers. Smaller institutions, like retail companies, commercial banks, and hospitals, then license those foundation models and execute the much cheaper, localized fine-tuning. General-purpose AI has essentially become a commodity. An institution secures a distinct advantage by applying its own proprietary first-party data to fine-tune these models for exact, domain-specific accuracy.